Well, hello and welcome. We here at Science Central have been very interested in studying this phenomena called weather. Right? So, let's see. Well, hello everybody. My name is Mac, and today we're going to be learning all about our wild weather that we have here on Earth. Now, if you wanted to study the weather on Earth, well then, you might look at different data sets or different imagery to help you predict what the weather is going to be like tomorrow, next week, and going forward. Now, if you were a meteorologist, not only would you look at the cloud cover here in infrared, which you all might be familiar with if you've ever seen a local weather meteorologist or someone who studies the weather, but also data that looks like this. Maybe you haven't seen it before. And when looking at this data, we might be able to guess that what we're looking at is wind speed, variable wind speed in our atmosphere. And if you wanted to study that further in meteorology, we also take a look at the circulation patterns that are most common on this Earth. You put in the circulation patterns. Obviously, you need to know the ocean currents because the weather above is fed by the oceans below. Now, also, obviously, you have the country borders, but the latitude and longitude, where are these things moving and where are they going? I don't know, tons of those things. Time zones, if you're wanting to communicate this, what is tomorrow? Because obviously, tomorrow in Japan is happening right now. So that's very important to understand. But all this can be quite confusing. So, today, my name is Mac, and we're going to be learning all about the weather. Now, as I said, the weather has to do with what's happening outside, when we go outside into our environments. Is it rainy? Is it dry? Is it hot? Ew. Or is it cold? So all these things are going to be discussed today, and we're going to break them down a little bit, starting with the idea of air pressure. So what I want you all to do is to take a big old deep breath in. Can everyone do that for me? Everyone take a big deep breath in. Now, blow it out. Now, what we just breathed in and out is the air around us. And the air around us is called our atmosphere, or an envelope of gas that surrounds a planetary body. Now that atmosphere can have different levels to it. But right here, on ground level, if you're not in a giant on the top of a mountain while watching me, about 70% of the air that you just breathed in is made of nitrogen gas. About 21% is made of oxygen. Now, you might have heard of that. Oxygen is quite important to us to breathe as human beings. And there's a lot of particulate matter that's floating up there as well. So a lot of different types of elements, dust, debris, smoke, pollution, all those things are also in our atmosphere. I want you to take a look here at this balloon. I have a balloon, and I can add some air to it here. Now, what I'm actually doing is I'm changing the pressure inside of this balloon. When I add more air inside of this balloon, there's more air molecules inside the balloon than there are outside of the balloon. So, we would say that there is higher pressure inside the balloon and lower pressure outside of the balloon. Now, something to note about our atmosphere and how air pressure works is that high air pressure always wants to equalize or become the same as lower pressure. So high pressure atmospheres like to disperse to go out into lower atmospheres. That's why if you release a balloon, that higher pressure wants to go out to where it's lower. So inside this balloon now, do we have high pressure, low pressure, or equal pressure to the atmosphere around us? That's right. We have equal pressure. It's not higher or lower inside of this balloon. Does that make sense? Okay. What would happen, though, if I just continued to put air inside this balloon? Would anyone like to see that? A bunch of high air pressure, and sooner or later, it just can't take it, oh, it didn't pop. Great. Phew, I thought it might. Now, if we want to look at the reverse of that, though, so we've shown you how high pressure inside of this sphere, like a balloon, wants to equalize into lower air pressure. But we can also take a look at the opposite, the inverse, the reverse of that. We can take a look at low air pressure and higher air pressure outside. Now, something to note about the air pressure that's on you and I right now is that there's a lot of it. There's over 60 miles of air above us. Our sky reaches over 60 miles high. So all that air is pressing down on us because of gravity. And there is a lot of it. In fact, if you take a look at your wrist, you can take a look at mine, but take a look at your own wrist. Now draw a 1-inch square, a 1-inch by 1-inch square on your wrist. It's pretty small, right? Now, there is over 14.7 pounds per square inch on every square inch of your body. So every square inch of your body has the equivalent of a bowling ball's worth of weight being pressed up against it. Can you feel that, though? Does it feel like there is a bowling ball on every square inch of your body? No, right? Why is that, though? Why can't you feel it? Well, one of the simpler reasons is because we have been born into this world and we're used to it. We have not only the pressure pushing in on us, but we have an equalized pressure pushing outward. So on every square inch of you, you also have an internal pressure pushing back. And so your body has found an equilibrium at this particular atmosphere. So you don't feel the effects. However, 14.7 pounds per square inch is a lot. That's pretty heavy. And one of the ways that we can demonstrate that is using this. Let me see. Can I zoom in here? These are called, these are called Magdeburg Hemispheres. So a hemisphere meaning half of a sphere. So these two halves of spheres or hemispheres can come together and create this little tiny ball. Okay? Now, right now, inside of this ball, we have the exact same air pressure on Earth as we do inside of it. Nothing's different. They're the same. And so when I close this ball and squeeze it really tightly together, I can easily take it off. However, you might have noticed that there's not only the two spheres, but there's a couple other things attached to the hemispheres. One of which is this rubber gasket here. So if I wet down this gasket just to make a really nice, clean seal, and we can talk about that later if there's time. If I put that on there and close this up, I've sealed it. Now, I have here a tube. And on this tube, I can connect to this vacuum pump. So this is a pump that takes the air out of something. If I can squeeze it on in there and turn on my vacuum pump, I can suck the air outside of the inside of this Magdeburg hemisphere, leaving low pressure inside. So if there's lower pressure inside because there's less air in there, then what's the outside? That's right, it's higher air pressure. Very cool. So let's suck some of this out here. Takes just a minute. Now you have to imagine, now that we're taking the internal pressure away from this, all 14.7 pounds per square inch is pushing inside or pushing onto the outside of this sphere. Because the atmosphere around wants to get inside of here. It wants to equalize. Higher pressure wants to equalize with the lower pressure. I think that's probably about good. So we'll turn that off and we'll take this off. Great. Now, if I've done this correctly, we have lower pressure inside, higher pressure outside. Mr. Gary, could I have some help here? I have two of these tug-of-war little grippy things. Could I have you socially distance? could I have you grab a hold of one of those and let's try and pull it apart, shall we? So we're full-grown adults. This shouldn't be too hard, right? Let's see. Gary? Okay. Whew. Well, I do probably need to hit the gym more frequently, but we were trying really hard there, and we could not get these two balls to separate. That's because there's a lot of external pressure being put onto these hemispheres. Now, I have a secret button, and if I release this button, it releases the pressure and allows me to pop open the hemispheres. Pretty cool, right? All right, so now that we've looked at a little bit of air pressure inside of there, let's take a little bit of time, and maybe Gary could come in and talk to us about our next segment. So, what are we looking at next, Gary?
We're looking at heat and the way particles move.
Oh, that's right. So I've been spending all this time talking about air pressure and high and low air pressure and how those kind of interact on our atmosphere. But to get a clearer picture, we do need to add in something with the weather. And Gary is exactly right. We need to talk about hot and cold. That's pretty important to us as human beings, right? Because we don't like things to be too hot and we don't like things to be too cold. So a good bit of data to know about the weather and to learn about how it works is the hot and cold molecules in our atmosphere. So, Mr. Gary, do you want to come in here and show us what's up?
Sure.
Great.
Can do that. All right. So for this part, I'm going to turn you guys all into air molecules. All right. We're going to use our fists to model the way air molecules like to move. So on the count of 3, 1, 2, 3, you are all air molecules. Now, let's move those fists around to demonstrate on how those air molecules like to move. Now, hot air molecules are like people. If you're hot and do you like being next to each other? Nah, you usually like to be away from each other. So hot air molecules like to spread out. They like to move. Actually, they like to go up into the air and spread out. Now, if you're a cold air molecule, they're again like people. When it's cold outside, do you like to be far away from each other or do you like to huddle together? Well, cold molecules like to huddle together to try to get warm. And those cold air molecules huddle together and they like to sink. So hot air rises, it spreads out, and cold air comes together and sinks. Imagine a hot air balloon. The way that a hot air balloon goes up into our atmosphere is that hot air that's being heated by the burners underneath the balloon heat that air up, and that air expands and it rises. So the balloon goes up into the air. Then, when they want to bring it down, they kind of turn off their jet and the burner, and then the air inside the balloon cools down. Those molecules come together, and then the balloon sinks because it's full of cold air. The next thing that we want to look at is now I'm going to turn you guys all back into yourselves. Now, I want you to use your imagination and imagine yourself being on your favorite beach during a bright, hot summer day. So the heat coming off of that sand is causing all of the air molecules around you to get warm. And they're moving and they're spreading out and they're rising up into the air. And then out there above the water, all those cold air molecules are clumping together and they're starting to come down a little bit. And then as they come down and that hot air is rising off the sand and the cold air is falling on the water, they start to shift because as the hot air goes up, the cold air moves in underneath it. And we start getting this circular pattern or the wind. And that's why when you're at the beach, you feel this cold wind moving in from off of the water because those hot air particles are moving up and those cold air molecules are coming in after it. And we get that nice wind motion. Now, Mr. Mack here has a demonstration on our sphere which kind of reiterates on how that hot air is rising and that cold air is falling. And it also has to do with our next part of the weather, how clouds are made. Mack?
Nope. Okay. All right. Good. All right. Good. So, clouds. You look up at the sky sometimes, and oh boy, howdy, there are a lot of clouds. But what are clouds made of? Well, clouds are made of moisture, right? Of water vapor. And that water vapor is actually coming off of our oceans, lakes, rivers. See, as the sun heats the earth unequally, which is to say, it heats the equator more so than it heats the North and South Pole, and it heats the daytime more than it heats the nighttime. All of that warm water can get evaporated. So have you ever heard of the term evaporation before? It's part of the water cycle. Evaporation is when that hot sun goes down. Oh, I can move this over. Hot sun shines down in those lakes, and some of that water actually evaporates, comes off of those lakes, right? And goes higher into the atmosphere. Now, as it goes higher into the atmosphere, the higher you go, the colder it gets up there. And as those water molecules begin to get really cold, they start, as Mr. Gary was saying, they start coming together. And as they start forming back together, they form up with a lot of the particulate matter that's up there, the dust and the smoke, and create clouds or condensation. Now, those clouds can only really hold so much water before the weight of them starts to get too much. And at that point, you can get precipitation. Or you can get, what's another word for precipitation? Rain, snow, sleet. You can get all that stuff. And when it hits the ground, there is a runoff there. So this is what we like to call our water cycle. And it's very important if we want to understand the weather. I also, if you don't like those, I have umbrellas. Umbrellas showing you the same process. Now, you can imagine those umbrellas being the air that's being pushed up. So as the warm air underneath of you starts evaporating that water, those water molecules fly higher and higher into the atmosphere. But again, as you go higher into that atmosphere, there's less molecules there. It starts to get colder, a loss of energy, and those start to turn into clouds. Now, the clouds are just a bunch of water that's stuck up there, and as the water starts to build up in the atmosphere, it will precipitate, or it will rain. It will sooner or later dump off all those water molecules into our skies, and then onto the ground. Very cool. All right, that makes sense? The umbrellas make it for you? Was it confusing, then the umbrellas helped? I hope so. I hope that cleared it all up there. Very cool. Now, if you wanted to make a cloud, what does it take to make a cloud? Now, I mentioned it a little bit earlier, but it takes 5 different things if you want a cloud to form. The first is you need water. The second is you need some kind of low atmosphere. So you need there to be a lower atmosphere. You need it to be a little bit colder. So if it's boiling hot, right, you're probably not going to get a cloud. You might get steam. But what you don't get is a cloud. So you need cold temperatures, low pressure. You need water. You need particulate matter or something for those water molecules to stick to. You need some kind of sticky agent. And so we talked in our atmosphere that you could have things like smoke or other dust, sand, those parts of tiny particles that are floating in our atmosphere. And the 5th thing is, what's the 5th thing? This jar? We do need this. We do need this jar. But what's inside this jar? Obviously, it's air. So you can't have a cloud without air. So I was never in a jug band, so I apologize. I can't do it. Anyways, you add some air in here. We already have some water, but I'll add just a little bit more here. Can't have clouds without water. I'm going to add some particulate matter in here, so I have some matches. Don't try this at home without adult supervision. I'm going to light some matches here and let those burn for a second. And again, I'm not trying to add in a lot of smoke like this is going to be a smoke jar, but I do want to add in enough of that soot in there for the water vapor to actually attach to. Now, what are some of the other things we needed? Oh yeah, it needs to be cooler, and we can cool off things by actually reducing the pressure on them, like Oh, like with this vacuum pump. Neat. All right, well, let me use this vacuum pump again. I'm going to try and create a tiny little vacuum in here. Remove some of that pressure inside of it. And we're going to see if I can make a cloud. Oh, that's not it. There we go. Ooh, already. Yeah, look at that. So that low pressure has made it easier for those water molecules there to come up, to rise up here and connect with all the soot and create that cloud. And I can take it off here, and it becomes clear again. If I put that vacuum seal back on and let it start to do its thing, all of a sudden you start to see that cloud re-emerge. Take the actual seal off, equalize the pressure, or make it the same as the outside. Clear as a bell. Pretty cool, right? Very nice. All right, Mr. Gary, what's next?
Well, we have a couple of graphics over there that tell you what you just demonstrated with that cloud.
Oh, all right, let's review. Thanks, Gary. So, on this graphic, you can see here high pressure and low pressure. Now, high pressure is that H that you're seeing, and the low pressure is the L. So, lower air pressure, that's when there's less of those molecules floating around, and it makes it easier for all of that evaporation or all of that water that's sitting on our puddles in our front yard, lakes, rivers, oceans, to come up inside of the atmosphere. So that lower pressure has all of those water molecules rising up. Now, if you have high air pressure, again, we're talking about what does high air pressure want to do? High air pressure wants to equalize itself. So you get a lot of clear, sunny days with high air pressure as that pressure is blowing down on us. So you can get some windy, sunny days there. The lower air pressure is what's going to make those clouds and ultimately those storms. Now, thunderstorms, though, Gary, is something that we should probably talk about, especially Science Central is in northern Indiana. So we get a lot of thunderstorms out there. To best understand thunderstorms, you need to have a clear grasp of high and low air pressure and hot and cold temperatures. And I have here another graphic on hot and cold temperatures. So whether you get snow or whether you get rain is dependent on the atmosphere around it. So if it's cold outside and you get those low pressure areas, that'll make snow. If it's warmer outside and you're under a low pressure area, you can get rain. Now, rain is just an accumulation of too much water stuck in those clouds that has to come out. But a thunderstorm, something more severe that we really want to keep an eye on, has to do with how those low and high pressure systems move against each other. So, Gary, if we could talk about that, and then I think we have one last experiment to talk about the most severe weather that we can get, at least here in Indiana, which is tornadoes. Gary?
All right. Yeah, as Mac was saying, it's that high pressure and that low pressure. Along those fronts, what we call when a weather system is moving in, if you have a high pressure system moving out or a low pressure system moving in due to the wind moving those pressure areas along, it's that area right in front where the storms are mixing. You've got the high and the low pressure mixing. You've got the warm and the cold air kind of coming together. And during these severe weather incidences and thunderstorms, you can get hot air. Remember, hot air likes to rise, trapped under cold air, because cold air likes to sink. And if you get a lot of hot air trapped under a bunch of cold air, that cold air is pushing that hot air down and the hot air is moving up. And that wind that we were talking about, that's moving sideways, starts to get pushed up onto its side because of that hot air rising with the cold air going down. And we start getting that vortex or that tornado cloud that you see, which is so dangerous when we have a tornado. Now, one of the things that's important to realize in this area is a tornado warning is a funnel cloud has actually been spotted, whereas a tornado watch is conditions are right. In other words, that warm air is rising, that cold air is kind of coming in above it, and we have the possibility that a funnel cloud could be forming. Now, tornadoes, the funnel cloud itself, are very dangerous. They can cause a lot of damage, but along with that funnel cloud is a lot of side damage, or what we call collateral damage, from debris that's flying around. That's why when they tell you to, during a weather warning, to seek shelter, you want to get out of the way of anything that might be flying around, especially during a tornado warning. Any small object can all of a sudden become very dangerous. So let's take a look at that with our severe weather demonstration wind machine back here. And what we're going to do is we are going to take a piece of drywall, standard household construction drywall. This is the covering of most of your walls on buildings. And we are going to see what happens if when we take a pencil and throw this pencil through the air at a high rate of speed and about a wind speed of about 50 to 70 miles an hour. So let's first take our Sharpie here and let's just draw a house on our drywall. We'll put the ground down here. We'll do just a small typical box-shaped house. Nice roof. Front door. Maybe a nice window so you can watch that weather come in. But remember, during severe weather, you want to be away from that window because those pieces of glass, if something would break that window, could be very dangerous. So let's put our house into our wind device. Pop that in there. Technical difficulty, but we got our house secured in our safety containment. Now, since we will be shooting a pencil, I'm going to wear my safety goggles. I'm going to grab our pencil, come down to this end. We're going to load the pencil into our machine. We're going to put our safety earmuffs on because we're going to be using some carbon dioxide as our wind. Let's hook that up here. It's a good test. And we're going to do a quick countdown. Ready? 1,